Yeah, my name is Ipo. I work for AWS. And today I'm going to walk you through the history of, where I'm going to talk about analytics, cloud analytics in particular. All right. I'm going to talk mostly about Redshift, Amazon Redshift, which is Amazon's proprietary cloud data warehouse. This is the only marketing slide I have, but the reason I have it is because of the public messaging we have put there. This is a quote we have put in public, and we have gone and said, that every day tens of thousands of customers use Redshift to process exabytes, plural, exabytes of data per day in AWS's infrastructure, which consists of 26 regions and 84 availability zones. So, we're processing exabytes of data from tens of thousands of customers in a global footprint. So this is a very large service, and it's really fun to be operating at that scale. And what this talk is about is I'm going to walk you through the history of the evolution of Redshift from its inception to where we are right now. And I'm going to focus a lot on how we use machine learning automation in order to make the service better. In particular, I'm going to walk you through history since 2013. Amazon launched Redshift as the first cloud data warehouse back in 2013, and the system was looking a lot like the one I have in the picture. And I'm going to walk you through kind of several years of evolution and show you how the system looks now, and the reasons we went and evolved this architecture to be looking a lot like that. So Redshift is a very large service. It's a big system. But if you squint, in general, you would argue that there are 6 big thematic areas, 6 topics where we are putting most of our energy on. The first and the most important, our job number 1, is security and availability. Our customers trust us to store exabytes of their data in our systems, and making sure that those are safe and and are available for them to process. So the job number 1 of any cloud data management service is security and availability. And one thing I like to ask when I am at this slide is, by show of hands, if you have to pick between security and availability, which one you would pick? Let me ask the students here.
With the favor of security.
Okay, yes, security is the job number 0, if you will. The most secure system is a system that it is down, because then you cannot take the data out of it. So yes, security is job number 1, and then the rest follow. All right. I'm not going to spend a lot of time now talking about security and availability, but if you want, I can answer questions at the end of the talk. The second big thematic area for us is performance. At the DNA of our system is we try to be the most, performant, better price performance of the analytic systems out there. In order to understand how we get good performance out of Redshift, let's look a little under the hood and understand how the system is designed. So Redshift consists. Are there any questions?
Are there questions from anyone? I don't see any show of hands here.
Okay. I'm sorry. All right. So the Redshift consists of kind of 2 separate layers: the compute layer and the managed storage layer. On the compute side, we have 2 types of nodes: the leader node, which is the one on the green box, which is the entrance of the customers to the system. So customers connect to this leader node using their tool of preference. Then there are a bunch of worker nodes or compute nodes, who are responsible for executing the statements they get. When a query comes in, we go through the typical phases of query execution. We parse the query, we do a bunch of logical rewrites to generate equivalent but more efficient query execution plans, and then we go to the cost-based optimizer, we pull statistics from the catalog, and we generate a distributed query execution plan that it is optimal, or we try to make it optimal. And we do a bunch of tricks there. For example, if the data has been partitioned, has been sorted, and you are joining two tables that are sorted on the join key between those two tables, then you can do collocated joins. You don't have to shuffle data around. Then, one thing that it is very unique and interesting in Redshift is that for every fragment of this distributed query execution plan, we go and generate C++ code that we literally open a C++ file and we printf highly optimized code that we use to execute the queries. So we generate this C++ code, we GCC compile it, and we take the executable, we send it down to the compute nodes, and the compute nodes start executing this query or this fragment of the query. The data from the managed storage layer are assigned to compute nodes given some distribution, and then the compute nodes start running their executable, processing the data they have been assigned. And we do all sorts of all the tricks in the book. We have zone maps or min-max pruning. We use vectorized SIMD execution to scan the data very fast from local, most of the time, local attached storage. We use vectorized friendly encodings, like in order to operate on data and compress data in a vectorized fashion. So we do all the tricks in the book. And by doing all these things, we achieve pretty good performance. Are there any questions? All right. In order to understand a bit more the process of code generation, let's take a simple query, such as the one I have here. What this query is doing, it applies a filter on one of the two tables, it joins two tables, and calculates an aggregate on top of that. A very simple query. What Redshift ends up generating is looks like a query fragment, code fragment that looks a lot like the one I have on the left-hand side of this graph, of this figure. You can actually read it. It's actually pretty easy to read. Right? You start scanning data, you pull two values, you apply a filter, you calculate, you probe a hash table, and that's it. And you calculate the aggregate, and you are good to go. In reality, we are not executing exactly the one I have on this. We do some additional tricks. For example, on the right-hand side, I'm showing you a trick we do in order to minimize data cache miss latencies, where we're keeping a buffer of values that fits in L1 cache, and we have a ring buffer, so we push at the tail of this buffer, we pop at the beginning, and we try to do that so that we are L1 cache resident. And on top of that, this code is a scalar code. We use actually AVX to vectorize the codes, not this scalar version. We do min-max pruning, we do late materialization. But at the end of the day, it is something that it is very, very efficient. It is almost as efficient as handwritten vectorized code. When I present this slide, people usually ask me, but don't you worry about the cost of compiling code inline during query execution? And the answer to that is yes, we do worry about that, but it heavily depends. Like if there is a query that takes minutes or hours to execute, spending a few seconds compiling a query is not a big deal, especially if you have to process, terabytes or more of data. But in cases where we have short-running queries, this cost may be very expensive. In order to minimize these overheads, we do all sorts of code caching. For example, one thing we do is on the leader node of every Redshift cluster, we have a cache of compiled code. And every time we generate C++ code, we check this cache and we try to reuse the compiled code. By doing that very simple trick, and because there is a lot of reuse of data of code queries in real life, this cache is very, very effective. In particular, we reach cache hit rates on compiled code in the order of 99.5% of the queries we execute on the fleet. But even that sometimes may not be enough. So one thing that we recently did, and we took advantage of operating as a global service such as Redshift in the cloud, was that we introduced a new optimization which we call compilation as a service. Which what it does, it is every time in the Redshift service we see a query fragment that we have not generated compiled code for that. We push this code fragment in a global microservice that essentially it's a bunch of worker nodes that compile this new query fragment, and they put the compiled code in a global cache. Anytime, any other future time that this query fragment needs to be executed in the fleet, the clusters go and pull from this global cache, and they don't have to compile this code. And checking this global cache is a few milliseconds, as opposed to seconds or several seconds that sometimes it takes to compile a query fragment. And by doing this very simple trick, we improve the cache hit rate of our compiled code from going from 99.5 to 99.96. And this is an optimization we could do because we are operating in the cloud in a global infrastructure. Does that make sense? Right. Okay. So we do all these things. Is there a question?
Got a question?
Okay.
So no, for a moment.
Okay. So we do all these things, and we are very much focused in Redshift in price performance, and we always obviously keep track of making sure that we offer the best price performance in the cloud. And this is a couple of graphs I took from a blog post that we posted recently, where we compare Redshift, the price performance of Redshift, against a bunch of other popular cloud data warehouses. And the benchmark we're using is the Cloud Data Warehouse benchmark modeled after TPCDS. And we have two different types of settings. On the left-hand side is what we measure as the out-of-box performance is the untuned performance, the one where the customer goes and defines the logical schema of the database, does not do any tuning, just loads the data and starts running the workload. In this example, Redshift achieves between 20% and 3.8 times better price performance than the other popular cloud data warehouses. And on the right-hand side is the tune performance, where we have a DBA fiddling with the database schema in order to squeeze the best performance out of that. And you can see that Redshift has provided the better price performance in both settings. Another graph that we really like is the one that measures the throughput of the system in presence of workloads that have short-running queries. One trend that we have been seeing recently, at least in the cloud analytics space, is that there is a lot of demand for workloads that are short-running, have multiple concurrent streams of short-running queries. And in this graph, we're showing the throughput of Redshift compared to other popular cloud data warehouses. And you can see that the throughput of the system is between 2 to 3 times higher throughput than the other vendors. Finally, the graph that I feel very happy about is this one. So what we did in this one, we tried to measure the scalability of the system as we increase the amount of data that need to be processed need to be processed. In particular, what we did is we took the cloud data warehouse benchmark modeled after TPCDS, and we increased the data size that it is being processed from 10 terabytes to 1 petabyte. So we increased the dataset size by 2 orders of magnitude. And we increased proportionally the amount of hardware we use. As you can see, the runtime of this benchmark remained pretty much the same, even though we went to 2 orders of magnitude more data. This linear scalability on the data size, given that you are increasing proportionally the hardware, is a very nice property. Our customers really like that because it allows them to have predictable costs and can do their planning and don't get unwindly high costs when the data set size increases or the throughput, the concurrency in the throughput increases. So we did all these things. Redshift was the first cloud data warehouse that was launched, and customers were very happy with its performance.
Maybe quick question.
Yes.
Do you have a sense for what are the main drivers behind those performance advantages?
I'm sorry, Manuel. There is a lot of echo. I don't know.
Can anyone switch off the sound?
I'm sorry, I hear you double. I cannot hear you.
Can you still hear me now?
Yes, now very good.
Okay, awesome. I was just wondering, do you have a sense for what are like the primary drivers behind those performance advantages compared to the other systems?
I mean, one of the bigger ones is this compiled code execution that it is kind of unique in Redshift that allows us to have super efficient code paths. Then it is, very interesting the storage format we are using, and this vectorized SIMD execution, optimized storage, the columnar storage we are using. So it is a combination. There is not a single, silver bullet that makes Redshift be very fast, but mostly a maniacal focus on performance and scalability. So we keep track of the performance of the system, and we are trying to push forward on making sure that the performance is the best out there.
Okay, sounds good. Anyone else has any questions on this?
I'm wondering what does the 4XL and 16XL mean?
Yeah. This is an instance. So Redshift is being offered in 2 different types of offerings. One is the provisioned version, where the customers pick the number of compute nodes in their compute environment and what type of these nodes will have. So those are instance types or sizes. And we also have a serverless offering, which is we pick on behalf of our customer the size of their computing environment. So this was on the provision side, where we specified how many nodes and what type they're going to have. But the whole point is that you can see that we went from 30 terabytes on 3 nodes to 1 petabyte on 100 nodes. And the time when it took from something less than 2 hours to something a little less than 2.5 hours. You increased by almost 2 orders of magnitude, and the time remained the same, given the proportionally increasing hardware, which is pretty good. All right. So we did all this. Performance was pretty good, and then customers came back to us and said, we really like Redshift, its performance, but we would like to store more data and have more concurrent users using the system. So that's what we did next. The biggest architectural change we did in Redshift over the recent years has been the introduction of the Redshift managed storage. Facilitated by AWS's Nitro hardware and high bandwidth networks that we're getting. We get instances that have 100 gigabit networks. AWS has announced instances that have 200 or 400 gigabit networks. So facilitated by these high-speed networks, we were able to disaggregate storage and remove it from local and take it from the local attached storage we used to have it and move it in a separate layer. And by doing that, we were able to innovate and iterate much, much faster, especially by separating the compute and storage. Once we did that, we were able to address all the scalability concerns on the side of storage. Customers could store petabytes of data within a single database, within a single Redshift environment. Then on the compute side, we did two things in order to improve the elasticity of the system. The first thing we did was the ability to elastically resize an individual Redshift computing environment. Customers are able to add or change the size of their computing environment by a factor of 4. They can go 4 times bigger or 4 times lower, and in order to hand-tune the size of the cluster and based on the SLA of their workload. So they can crank up or crank down the system, and they can tune the latency of their individual queries. And when they are happy with the size of that, there will still be cases where there is a burst of activity. So a bunch of requests coming, say, on Monday morning, Monday morning, everybody goes to the office and wants to run their queries. In these cases, there will be some finite, because any computing environment has finite capacity, you have to say, okay, I cannot admit more concurrent requests because I will start thrashing. One thing we did in order to address this situation was to introduce something that we call, which is an auto-scaling feature, which we call Redshift concurrency scaling. And the way it works is that when a computing environment starts admitting requests, and at some point it is clogged, they cannot process admit more concurrent requests, and the customer chooses to, we pull in additional equi-sized clusters, and we start spilling over requests to these additional clusters in order to auto-scale and process more requests concurrently. And the interesting thing with that is that the customer does not have to change their application. They connect to a single endpoint, they keep on connecting and submitting queries to one system, and the system, auto-scales and then contracts when the flurry of requests goes down. And this thing is, again, it works pretty seamlessly for the customers. In this graph, I'm plotting the throughput a customer could get when they were running. This is an experiment we did in the lab, where we were running the cloud data warehouse benchmark derived out of TPCDS. And what we have on the x-axis is the number of concurrent users that are submitting queries from this benchmark with 0 think time. So that emulates a quite stressed environment where customers submitting requests all continuously. What you can see is that at the beginning of the year 2019, the maximum throughput a customer could get out of this workload was approximately 200 queries per hour out of 5 concurrent users. We rolled out this auto-scaling feature and we kept on iterating. And by the end of the year, the customers could get over 12,000 queries per hour from 210 concurrent users. And I think at that point we stopped this experiment because it could go more, but we just we stopped pushing it further. And 210 concurrent users with 0 think time emulates thousands of concurrent users in a realistic scenario. So we were able to improve the throughput of the system by a factor of 60 within a year, without the customer having to do a single change in their application. And this is kind of quite impressive. And this is kind of the power of the cloud. You were able to provide almost infinite scalability without having to do anything. Whereas in the old days, in the on-prem world, you had to go through several months or years of procurement things in order to be able to get this type of increase in throughput. And when we did that, by doing ability to elastically resize any computing environment and auto-scaling, we were able to address the scalability needs, compute elasticity needs of any individual Redshift environment. But then what the customers told us is that they would also like to have independent environments to be able to add more environments and run their own workloads. For example, if they have different business units or different teams, they want to have their own separate environment to experiment, and at the same time have access to some reference data sets that that are transactionally maintained by some centralized authority. So what we did there was we introduced a feature in Redshift that we call data sharing, which allows customers to be able to set up individual environments and consume from a centralized producer cluster. And those environments can auto-scale independently and in isolation to the other clusters. And by doing that, we have now the ability to have thousands of concurrent users on every environment and then pop up additional environments on top of that. And we can do that between clusters in the same account, between clusters across accounts, or between clusters even across different regions. So we can have a globally global available data sharing capability that offers also serializable snapshot isolation, which is what Redshift is offering as the default isolation level across the globe. So this is pretty interesting, and customers really like it. So by doing all these things on the storage side and the compute side, we were able to address all the elasticity needs of our customers. Then the next thing they asked us is, we really like Redshift, but it is a traditional cloud data, it's a warehouse, it's a data warehouse, but we have all these other sources of data that we would like to access and use them for our day-to-day analytics. So that's what we did over the years. So the first thing we did was to integrate with Amazon S3. Customers really like S3. It's the most scalable storage layer in the cloud, and customers put a lot of data in open file formats in S3. So by introducing, what we did was we allowed the Redshift customers to be able to run queries on and combine data from the warehouse as well as in open file formats in S3. But they also have, as Amazon, we have also this very popular and very scalable operational databases, such as RDS Aurora and RDS MySQL and Postgres. So we added the ability for our customers to be able to federate queries and submit queries and access the data in these operational databases. We also added the ability to do streaming ingestion so that you can have your streams like Kinesis streams or Kafka streams and stream the data into Redshift directly and be able to query the data very fast. So now our customers are able to run queries between their open file formats in S3, their warehouse, as well as the operational store in one single SQL interface, which customers really like. And because that was very good, but then our customers told us we would also like to run machine learning on top of our Redshift data. We would like, in particular, to both train our models and run inference within our environment. And we did that by integrating with Amazon SageMaker. And the way we do it is very interesting, and I would be happy to talk about it at the end. And in order to offer us ability to have a generalized execution environment, we also integrated with Lambda. So the bottom line is that we took back from what Redshift was back in 2013, which was a traditional warehouse, to a system that it is very well integrated and connected with a very broad and powerful set of services at AWS, from open file formats and lakes to operational stores like Aurora, to streams, to machine learning and Lambda execution. Okay. That was good, but what customers were very happy. They said, we really like the integration with the AWS ecosystem. We like the elasticity of the system. We like its performance. Still, Redshift requires some fiddling. It requires us to have some administrators in order to maintain the systems and make the best performance, to squeeze the best performance out of them. So a large fraction of our energy and our resources is being spent into making the system as simple to use as possible by using machine learning. If I have to think about and categorize how we use machine learning in Redshift, I would argue that it is that we use machine learning in 4 different areas. The first one is in operations. As I told you earlier, Redshift runs in AWS's global infrastructure of 26 geographic regions and 84 availability zones around the world. In order to maintain such a large fleet of clusters and having tens of thousands of customers processing exabytes of data, there will always be something that may not be going well. There will always be some issue, either hardware, either software, somewhere around the globe. So being able to maintain operational health is a very big challenge for us. And one of the most interesting challenges, so there are 2 types of errors. There are the errors where something is dead, like you ask, are you dead? Are you alive? It pings yes. Are you alive? Yes. Are you alive? At some point, you don't hear something. Are you alive? Second time, you may not hear, but something at that point, you'd realize that this other side is dead, and then you kick off your auto remediation and you're good to go. You go back to a healthy system. What it is more challenging is when you have gray errors. Say some spindle is not spinning as fast as you want, or some router is dropping packets left and right, or some NIC is not well attached to the board. When you start, the system start going slower, but you don't know, is it slow because there is a hardware failure, or it's because the customer stopped running requests in this system. So being able to identify with confidence these gray errors is something that requires a lot of work. And we have been using machine learning to identify these outliers and gain the confidence to either page an operator and tell this operator, go and check what's going on there, or automatically kick off this auto remediation functionality. The second area where machine learning is great is, again, in resource management at scale. We as database operators in the cloud do, one of the things we do is we maintain pools of hardware available and ready for when our customers come in and request that. So when, say, in Monday morning, when all the customers go back to their office and start running queries, we need to have a lot of hardware ready for them to be able to pull the hardware and start running their workloads. And the interesting observation here is that the usage patterns of our customers are pretty predictable. So I could not put the X graph here, but this is one graph that shows the usage of one of our services, and you can see the very periodic access pattern the very periodic behavior that you can see here. And obviously the dips are the weekend, right? So during the weekend, things drop, and then over the week, things pick up. If you have this type of predictable behavior, you can be very smart in creating pools of hardware and have it and size these pools according to the expected demand. And by doing so, not only you are able to improve the utilization, you don't have to be wasting a lot of hardware that sits there idle, but at the same time, when your customer needs their hardware, you can have it up and running ready. So in this graph, I'm plotting the Whirlpool hit rate that in our service. This is a graph we posted back in 2020, where we added machine learning prediction and forecasting in order to improve the utilization of our whirlpools. And you can see that the hit rates improved substantially once we started adding forecasting in our algorithm. Those are those two areas of usage of machine learning are in the area of large scale of as we operate the service at a very high level. But we also use machine learning within the system, within the database. In particular, we do it in two areas, one in the tuning area and the second one in the area of workload management. So one thing we do in Redshift is we monitor the activity of the system, we see what the customers are running, and at times of low activity, we kick off maintenance operations that previously were a responsibility of a database administrator to do. So, for example, we monitor the system and we may decide that it is a good time to run an analyze or vacuum a table or build a materialized view or change the distribution key or the sort key of a table. And we do that by monitoring the workload and ranking all these maintenance operations that there is a backlog for operations that we would like to do, and we start executing them at priority of the one that it will have the biggest impact for our customers in order to make the workload run faster. In order to make these calls, to do this kind of intrusive changes, you need to have good signals. So we spend a lot of time trying to find algorithms that improve the performance of the system. So, for example, there is this paper from VLDB in 2020 where we describe the algorithm you use in order to decide what is the optimal distribution key of the tables in the system. And with the way we do it, we model it as a graph problem where the edges are kind of the joints we monitor, we see executed in the system and how many rows need to be shuffled. And then we try to minimize the weight in this graph. And by doing that, so initially we took that, we start understanding that our recommendations make a lot of sense. And then we took it to the next level where we not only make a recommendation to the customer, hey, customer, we monitor and we suggest you to go and change the physical design of your database because we feel that it would be better. But we go and we actually do take initiative and make this physical change, even though the customer was not involved. So this graph, I'm plotting the latency of a Redshift cluster running the TPCH at 30 terabyte workload. When he asked Redshift to manage the physical design of the tables by itself. And you can see that within two days, within 48 hours, the time it was taking to run this workload improved from 100 minutes to 60 minutes. So the system became 2x faster, almost 2x faster, without the customer needing to be involved at all. We just monitor the workload and make the physical design changes that improve the workload. And now we're taking this one step further by not only changing the physical design of the database of the tables, but also we go and create or drop materialized views when we see them fit. We are quite conservative, but when we pick patterns that we believe that creating a materialized view would be beneficial, we go and do it. This is some of the things you can do in the cloud that you could not do in the traditional on-prem databases. And the last area where machine learning is great is for workload management, for scheduling and predicting sizes of jobs. So one thing that we did is, if you think of a database as a queuing system where it has to process small jobs and big jobs, the best way to increase the throughput of the system is to admit the small jobs before the big ones. And that's a very simple classifier. So that's what we have. We have a classifier. Whenever a query comes in, we classify it and we decide very quickly whether it's a short-running query or a long-running query. And we take the short-running queries, we admit them in the system without admission control, and then we have some admission control for the longer-running ones. That is something that has been running in production for many years now. The next thing we did, not only we try to predict if it is a long or a shorter or long query, but we also try to predict how many resources this query needs, like how much I/O, how much CPU, how much memory. And by getting confidence on the expected resource consumption of the queries, we are able to admit more queries into the system, try to maximize the utilization of the resources in the cluster. And by doing all this, we're able to increase the throughput of the system using this classification. So we did all this, autonomics, customers were happy, but they told us, they came back and told us, we really like what we get in Redshift, but you're still asking us a question of to decide how many compute nodes I will have in my computing environment and what instance type. Can you please take these decisions away from me? And that's what we did. So we took all this system that we have built over the years, and we overlaid an intelligent dynamic compute management environment, management system, and we hid all this complexity behind the serverless interface. So we added the ability, we monitor the workload, we decide what kind of compute environment we're going to use for the customer. We auto-pause and auto-resume it when customers are not using it and using it. And we charge our customers for the seconds they use this system. We keep the remaining of the functionality the same, so customers can query their streams, their operational databases, they can use machine learning, they can share data with other clusters. But we take on the challenge of providing compute resources for our customers, auto-scaling them and whatnot. And this is where we are right now. Okay, sorry. This is where we are right now. So over the past 40 minutes or so, 45 minutes, I walk you through kind of the history of Redshift, which is one of the most popular cloud data warehouses. Every day we have tens of thousands of customers using Redshift to process exabytes of data. We are very focused on the price performance of the system. We take pride on, we offer the most scalable and fast data warehouse out there. We have the ability to store petabytes of data, tens of petabytes of data within a single environment and have thousands of concurrent users using the system. And we have a very tight integration with the broad environment of AWS services. And we use machine learning everywhere. We try to use machine learning and introduce autonomics that make Redshift easy to use and don't have to have administrators being involved. And we are offering that also recently. We started since this summer, offering this packaging of Redshift in a serverless experience that has an intelligent compute management layer on top of that. And as we like to say at AWS, it's still day one. There is a lot of innovation to be made in the cloud, and we are very excited about where we are in the future. And, kind of mandatory, I have to tell you that we are hiring. We have in Palo Alto, Seattle, Boston, in Berlin, in Sydney, and in Dublin. We have a lot of engineering positions for us, for many of the future engineers to come and join us. And that will conclude my talk. Thank you.